welcome to Talkcast, episode 1 of another new series. So at the moment I'm juggling essentially 3 series, concluding the beginning of Infinity, chapter explorations. I have just commenced and just recorded the first episode of the Science of Can and Can't, the popular science book. In addition to being a popular science book, it's a groundbreaking, revolutionary exploration of constructor theory, a new physics theory by Chiara Mileto, who's the author of the book, and David Deutsch, who is the originator of the theory. And now I'm beginning for the first time an exploration of David Deutsch's first book, The Fabric of Reality, the book that introduced me to the work of David Deutsch and really changed my mindset in ways more fundamental than I think anything else that came before. And it may seem odd that I'm doing 2 books in parallel, but my reason for that is twofold. I can't wait for either of them. I want to do both. Now that I'm finishing up with the beginning of Infinity, I've been, in my mind, I've prepared myself for doing The Fabric of Reality. And the fact that Chiara has just released this book, it really means that I can kind of bookend the beginning of Infinity with its predecessor, which is The Fabric of Reality. And in some sense, its intellectual successor, certainly a descendant of a kind, which is The Science of Can and Can't by Chiara. But this one is about The Fabric of Reality. So let me get into The Fabric of Reality. Let me first explain why The Fabric of Reality is so exciting. And I've said this many times before in many different places and different forums, but the basic thing is that I have a number of popular science books here on the bookshelf behind me. Dominant among the authors there is Paul Davies. And Paul Davies wrote some wonderful books that were summaries of our best understanding of science at any particular given point in time. And he would connect these, unlike many other authors, he would connect these to the history of ideas and to philosophy and to other areas of our intellectual endeavors. Things like religion, theology, mathematics, chemistry. He would explain how physics is tied into these different areas. But what I would say about that is it provided a wonderful overview, an exciting overview of some of the latest parts of science, especially in physics, some of the mysteries, some of the open questions as well. But it is they were the kind of books, broadly speaking, that anyone who read them, anyone knowledgeable in those areas would probably think is uncontroversial. This is different to David Deutsch's work. David Deutsch's Fabric of Reality is not merely a summary of extant knowledge, the stuff that everyone agrees on. It is taking the best theories and explaining them, number one, how they are, in a sense, a coherent whole, hence the fabric of reality, and how there is a particular way that one should understand these things in realistic terms. And so the Fabric of Reality is about the 4 strands, so they're talked about, the 4 strands of the Fabric of Reality. And David takes a scalpel, a scalpel to trying to remove errors from our understanding of these different theories in order to clarify exactly what our best understanding is, as hard as it may be sometimes to accept. And, in particular, the theory of quantum physics is explained here in a popular account for the first time, as far as I'm aware, first time in a popular account. We explain the realistic conception of quantum theory. Prior to this, as I was struggled through university trying to understand quantum theory, I was told the usual nonsense about if you think you understand quantum theory, then you don't. Okay, this is what Richard Feynman said. What David Deutsch does is he acknowledges the existence of various other so-called interpretations. And one of the books I have up here, right here, is The Ghost in the Atom by Paul Davies and Julian Brown, by another author and Paul Davies. And they go through just about every interpretation of quantum theory that existed at the time of the publication of the book. This was back in the late 80s. One of the people they interview is David Deutsch, and in that book, he does try to explain the many worlds interpretation of quantum theory, what was called the many worlds interpretation of quantum theory at that time. And at that time, I was still struggling to understand it, and I didn't really understand even that explanation. But here in The Fabric of Reality, we get an explanation of quantum theory that is just as clear as one can hope for at the time, and even through to today. It is still my go-to explanation for how to understand quantum theory. And there's only one way to understand quantum theory that we know of, and that is the existence of quasi or semi-parallel universes where there are entities existing in those other universes which we don't have easy access to except through interference experiments and so on. That's explained in this book. And that's the thing that really hooked me for sticking with the book from beginning to end and being wowed on almost every other page. But the thing that drew me in, that was the thing that sort of enticed me to continue reading, but the thing that drew me in was chapter 1. Chapter 1, where David sort of seemed to dive into my own psychology somehow. Because, again, this book was published in 1997. And at the time I was doing, at uni, undergraduate, doing physics, doing mathematics, doing philosophy. And kind of having the sense that there has to be a way in which all of this comes together. I kind of somehow subconsciously accepted that reality was just a coherent whole out there that you could come to have a better and better understanding of, that it didn't have to make no sense. But at the same time, everyone seemed to be aspiring for specialization. So the more that you knew, the more that you specialized. So I was interested in astronomy, but astronomy wasn't enough. You needed to be an astrophysicist, but that wasn't enough. You needed to be an astrophysicist interested in stars, but that wasn't enough. You needed to be an astrophysicist who was interested in variable stars, but that wasn't enough. You needed to be an astrophysicist who was interested in variable stars called Cepheid variables, and you had to use them in order to find the distance to distant galaxies. And so you would become ever more specialized as someone who gained more and more knowledge. This seemed disappointing to me. I wanted to be more broad than that. I wanted to have a broad understanding of everything. And that leads me to the beginning of the book. And so I'm just going to dive in, and we'll come back to what the other strands of the Fabric of Reality are. But this is what David says in chapter 1 of the Fabric of Reality, titled The Theory of Everything. And David writes, I remember being told when I was a small child that in ancient times it was still possible for a very learned person to know everything that was known. I was also told that nowadays, so much is known that no one could conceivably learn more than a tiny fraction of it, even in a long lifetime. The latter proposition surprised and disappointed me. In fact, I refused to believe it. I did not know how to justify my disbelief, but I knew that I did not want things to be like that, and I envied the ancient scholars. It was not that I wanted to memorize all the facts that were listed in the world's encyclopedias. On the contrary, I hated memorizing facts. That is not the sense in which I expected it to be possible to know everything that was known. It would not have disappointed me to be told that more publications appear every day than anyone could read in a lifetime, or that there are 600,000 known species of beetle. I had no wish to track the fall of every sparrow, nor did I imagine that an ancient scholar who supposedly knew everything that was known would have known everything of that sort. I had in mind a more discriminating idea of what should count as being known. By known, I meant understood. The idea that one person might understand everything that is understood may still seem fantastic, but it is distinctly less fantastic than the idea that one person could memorize every known fact. For example, no one could possibly memorize all known observational data on even so narrow a subject as the motion of the planets, but many astronomers understand those motions to the full extent that they are understood. This is possible because understanding does not depend on knowing a lot of facts as such, but on having the right concepts, explanations, and theories. One comparatively simple and comprehensible theory can cover an infinity of digestible facts. Our best theory of planetary motions is Einstein's general theory of relativity, which early in the 20th century superseded Newton's theory of gravity and motion. It correctly predicts, in principle, not only all planetary motions, but all other effects of gravity to the limits of accuracy of our best measurements. For a theory to predict something in principle means that the predictions follow logically from the theory, even if in practice the amount of computation that would be needed to generate some of the predictions is too large to be technologically feasible, or even too large for it to be physically possible for us to carry it out in the universe as we find it. Pausing there, just my reflection. And going back to where David talks there about this idea that knowing everything that can be known can't possibly be about, for example, knowing where all the astronomical bodies that orbit the sun, or the stuff in the solar system, what orbits they're going to take at any particular moment. In other words, if you ask me now, where is Mars going to be in relation to the Earth as it orbits the sun tonight at 9 p.m. as I look into the sky, what part of the sky will it be? I won't be able to tell you. I won't know that. In fact, I won't know anything except the moon. I've got a good idea where the moon will be tonight. But that's not the kind of knowledge we're interested in. What we're interested in is the understanding. Could I find out? Yes, well, there's a number of ways I could find out, but could I understand the laws? Yes, I've studied those laws, and anyone who wants to study those laws can study those laws of orbital motion, of being able to predict, given certain quantities, okay, given certain things like the mass of the sun, the distance between the sun and the object orbiting it, okay? These are the kind of bits of information that can go into the laws as we understand them to enable a prediction. And therefore an understanding, a deeper understanding, that in fact all these bodies that go around the sun follow elliptical orbits. And if you have a sufficiently powerful computer, it will do the calculation for you. You can do it with pen and paper. If you want high precision, then a computer is much better, as David says. And that's where the understanding is. Just understanding that this equation represents this particular physical entity, be it space-time or in Newton's conception, the force of gravity. Then given positions of objects and masses of objects, then you can figure out what's going to happen to them over time. This is the understanding that physics gives us. So far from causing the number of things to be remembered to proliferate, understanding a simpler, deeper law that underlies all those facts is far more illuminating, and it requires less memory as well, doesn't it? Okay, back to the book. And we're just about to get into a section where David is going to depart, following Popper, from so many of the rest of physicists as they understand physics. And specifically because this debate centers around, of course, quantum theory, as we will come to. And this is why one of the motivations for why he says what he's about to say. And what he says is, quote, being able to predict things or to describe them, however accurately, is not at all the same thing as understanding them. Predictions and descriptions in physics are often expressed as mathematical formulae. Suppose that I memorize the formula from which I could, if I had the time and inclination, calculate any planetary position that has been recorded in the astronomical archives. What exactly have I gained compared with memorizing those archives directly? The formula is easier to remember, but then looking a number up in the archives may be even easier than calculating it from a formula. The real advantage of the formula is that it can be used in an infinity of cases beyond the archive data. For instance, to predict the results of future observations. It may also yield the historical positions of the planets more accurately because the archive data contain observational errors. Yet even though the formula summarises infinitely more facts than the archives do, knowing it does not amount to understanding planetary motions. Facts cannot be understood just by being summarised in a formula, any more than being listed on paper or committed to memory. They can be understood only by being explained. Fortunately, our best theories embody deep explanations as well as accurate predictions. For example, the general theory of relativity explains gravity in terms of a new four-dimensional geometry of curved spacetime. It explains precisely how this geometry affects and is affected by matter. That explanation is the entire content of the theory. Predictions about planetary motions are merely some of the consequences we can deduce from the explanation. Now, I think that there bears repeating. Speaking about the general theory of relativity, David said, that explanation is the entire content of the theory. predictions about planetary motions are merely some of the consequences that we can deduce from the explanation. Okay, so my reflection on that. Here in the Fabric of Reality, David is holding up as brightly highlighted as anywhere the centrality of explanation to the project of science, and even more broadly. But when I first read this book in 1997, I think I appreciated the negative aspect of David's argument, namely that science wasn't only about prediction. I think I got that. That science wasn't just a list of facts. I think I got that. What I don't think I really took on board was what the significance of explanation really was. And even later, when I read some Popper for the first time, I still didn't quite understand the centrality of explanation. It wasn't until the beginning of Infinity, when David explained for the first time that what we're after, whether it's in science or anything else, is not an explanation of any kind, because explanations are a dime a dozen, but hard-to-vary explanations. Hard-to-vary explanations. And it's the hard-to-vary explanation that makes an explanation a good explanation. But I just say that because it's an interesting, personal, for me, psychological phenomena. That the concept of explanation was very much here in the Fabric of Reality. But it took me a decade or more to really understand what was being said here. And now I think I do have a much better understanding of what was going on there. As much as I took from the Fabric of Reality, as fundamentally ground shifting in terms of the perspective change that I underwent having read this book, I still didn't pick up everything. And that's kind of a remarkable thing. And I think this is why people do go back to great books. And this is what distinguishes great books from lesser works, let's say. That you can keep returning to these books and figuring out that there's yet more to learn and that you missed so much the first time around. And like I say, the importance of explanation here that David is highlighting seemed to have escaped me. It really did escape me to a large extent. I understood what scientific theories were not, but I don't think I really got what scientific theories were. And I'd been reading about, science and studying philosophy all this time, all the way up to the beginning of Infinity. So I think it wasn't until actually, even just slightly prior to the beginning of Infinity, it was in one of David's TED Talks, A New Way to Explain Explanation. I think it was then that the light bulb moment happened for me the first time I saw that. But I guess I shouldn't be too hard on myself. After all, there are professional scientists out there, greatly accomplished physicists, that I do not think appreciate what a good explanation is, or the importance of explanation at all. Well, we know this is the case because, as we're going to come to in the Fabric of Reality, as we've covered somewhat in the Beginning of Infinity series, well, we've covered a lot in the Beginning of Infinity series, there is a certain kind of theoretical physicist, and it seems to infect theoretical physics more than anything else. A certain type of theoretical physicist, specifically interested in, let's say, quantum theory, that thinks that explanation is overrated. And what we're after, of course, is prediction, and merely prediction. This is the era of what's called instrumentalism, that all you want out of a theory is to be able to predict the outcome of experiments. And this is a completely misconceived notion as to what science is about. I mean, no one would be tempted in almost any other area of science to think that this is what science is about. No biologist is interested in trying to predict which species are going to evolve. They're interested in understanding the explanation of the origin of extant species and even extinct species as well. In chemistry, we're interested in the explanation of combustion, not all the ways in which fires might occur in the future. We're not trying to predict all the fires that are going to happen. In geology, we're interested in understanding, unifying things like volcanic eruptions, earthquakes, the drift of continents. And although we'd like to be able to predict things like earthquakes, we can't at the moment, that's not the whole point of geology. Geology is understanding the differences between rocks, how rocks come to have the different chemistry that they have within them, the age of the Earth, how a planet can be dynamic or not. We want to understand which is to say, we want to explain. But it is just in certain rarefied areas of theoretical physics that apparently the rules need to change because some people are uncomfortable with literal explanations, or they simply lack an explanation. So beware, beware that kind of physicist, because it seems to be in physics alone, where explanation is pushed aside. But I shouldn't say only, okay? Of course, we have a certain kind of scientism that's out there now as well. So there is a lack of willingness to understand, let's say, how economic systems work or how psychology works. And instead we're engaged, rather too much of the time, in attempting to predict the behavior of people, the behavior of economic markets, rather than understanding what it takes in order to, let's say, create wealth in economics. What are the preconditions for creating wealth? What has worked in the past and why has it worked in the past? Can we rule out some economic theories? Instead, some people just want to plot graphs in an attempt to predict what is going to cause the stock market to rise or not, and then fiddle with the knobs in some way or other. And this is an instrumentalist view, I would suggest, within economics. And of course, we have historicism, this idea, this false idea, this dangerously false idea, that by looking at the past, we can extrapolate through to the future, especially in the realm of politics and history and sociology. And this leads to some terrible political movements. So I'm probably a little bit unfair to say that it's only the theoretical physicists who do this. Yes, it appears in psychology and history and the humanities and the social sciences. It does appear there as well, this reluctance to really grapple with an understanding of things and being a certain degree humble in the face of not having an answer, of being able to say, we don't know, we are ignorant here, but let's do the best with what we do in fact know, but not pretend that we have already everything tied up into a nice neat little bundle where we can extrapolate off into the future. Because the risk, of course, with extrapolation is it is an application of the false mode of reasoning, which is induction. And there is absolutely no way that you can rule out the next observation that you make isn't going to refute your entire linear trend or whatever other trend you think that you have in hand. Instead, as we say here, and as David is explaining here, the only way to make predictions, reliable predictions which are genuinely logical deductions and which allow you to assume that what you know now will happen into the future, is to have a good, hard to vary explanation. Of course, good and hard to vary do not yet appear here in the fabric of reality. But the idea of a prediction is we're deducing it from an explanation. And more than that, it has to be a good explanation. And specifically, the system has to behave in such a way that you know that it has universal laws governing it, such that the extrapolation is not going to be affected by things like, for example, knowledge creation. Yet. And so this is why general relativity allows us to predict the motion of planets. Why? Because we can reasonably, at this point in the history of human civilization, assume that the only thing affecting, for example, the motion of planets in our solar system around the sun is the curvature of space-time, is gravity, explained by the general theory of relativity. And therefore, we can make a deduction from that theory, which we call a prediction, and predict where any of the bodies within the solar system are going to be from moment to moment, using general relativity. Now, can we make a prediction, a reliable prediction, for what those planets are going to be doing 1 billion years from now? No. No, for a whole bunch of reasons. Because we cannot assume, in the trivial case, that some other large cosmological body isn't going to cause a collision with the objects within our solar system. So that's a simple thing. Our ignorance about what else might happen to the solar system into the distant future. A comet could come. A stray neutron star could go wandering through the solar system. Who knows? But the more optimistic view is, as we learned from the beginning of infinity, we don't know what human civilization is going to be like 1 billion years from now. 1 billion years? Will we have the power to move planets out of their orbit? Will we want to do so? Perhaps. Perhaps we will have mined Mars such that it no longer exists, basically, and we've converted it entirely into a super colony that travels across galaxies. I don't know. But the point is, we can't just solely rely upon something like general relativity to predict the orbital motion of planets into the far, far distant future. We can do it for the next few years, reasonably, with some reasonable accuracy, we would presume. Okay, let's go back to the book. David writes, what makes the general theory of relativity so important is not that it can predict planetary motions a shade more accurately than Newton's theory can, but that it reveals and explains previously unsuspected aspects of reality, such as the curvature of space and time. This is typical of scientific explanation. Scientific theories explain the objects and phenomena of our experience in terms of an underlying reality, which we do not experience directly. But the ability of a theory to explain what we experience is not its most valuable attribute. Its most valuable attribute is that it explains the fabric of reality itself. As we shall see, one of the most valuable, significant, and also useful attributes of human thought generally is its ability to reveal and explain the fabric of reality. Pausing there, just emphasizing that. So here, in the fabric of reality, we already have a hint of the importance of people and the importance of human thought there. One of the most valuable, significant, and also useful attributes of human thought generally is its ability to reveal and explain. Fantastic. So there we go. Are we getting the nascent beginnings of the universality of the human mind? I think so. I think the hints are there. The ground is being set. And there also, where David writes, the underlying reality, which we do not experience directly, is the first shot across the bow of empiricism. Okay, this great misconception that so many scientists and philosophers and I guess men on the street still holds, that the way in which science works is that we go out and we observe stuff. And in observing stuff, we derive knowledge from nature in some way. This is a misconceived way of thinking about the project of science or knowledge generally. This is not the way in which knowledge is constructed. It's a creative endeavour. So let's continue with the book. David writes, yet some philosophers, and even some scientists, disparage the role of explanation in science. To them, the basic purpose of a scientific theory is not to explain anything, but to predict the outcome of experiments. Its entire content lies in its predictive formulae. They consider that any consistent explanation that a theory may give for its predictions is as good as any other, or as good as no explanation at all, so long as the predictions are true. This view is called Instrumentalism, because it says that a theory is no more than an instrument for making predictions. To instrumentalists, the idea that science can enable us to understand the underlying reality that accounts for our observations is a fallacy and a conceit. They do not see how anything a scientific theory may say beyond predicting the outcomes of experiments can be more than empty words. Explanations, in particular, they regard as mere psychological props, a sort of fiction which we incorporate in theories to make them more easily remembered and entertaining. The Nobel Prize-winning physicist Steven Weinberg was in an instrumentalist mood when he made the following extraordinary comment about Einstein's explanation of gravity. Quote from Weinberg, quote, "The important thing is to be able to make predictions about images on the astronomer's photographic plates, frequencies of spectral lines, and so on. And it simply doesn't matter whether we ascribe these predictions to the physical effects of gravitational fields on the motion of planets and photons, as in pre-Einsteinian physics, or to a curvature of space and time." Gravitation and Cosmology, page 147, end quote. Weinberg and the other instrumentalists mistaken. What we ascribe the images on astronomers' photographic plates to does matter. And it matters not only to theoretical physicists like myself, whose very motivation for formulating and studying theories is the desire to understand the world better. I am sure that this is Weinberg's motivation too. He is not really driven by an urge to predict images and spectra. For even in purely practical applications, the explanatory power of a theory is paramount and its predictive power only supplementary. If this seems surprising, imagine that an extraterrestrial scientist has visited the Earth and given us an ultra-high technology oracle which can predict the outcome of any possible experiment, but provides no explanations. According to instrumentalists, once we had that oracle, We should have no further use for scientific theories, except as a means of entertaining ourselves. But is that true? How would the oracle be used in practice? In some sense, it would contain the knowledge necessary to build, say, an interstellar spaceship. But how exactly would that help us to build one, or to build another oracle of the same kind, or even a better mousetrap? The oracle only predicts the outcomes of experiments. Therefore, in order to use it at all, we must first know what experiments to ask it about. If we gave it the design of a spaceship and the details of a proposed test flight, it could tell us how the spaceship would perform on such a flight, but it could not design the spaceship for us in the first place. And even if it predicted that the spaceship we had designed would explode on takeoff, it could not tell us how to prevent such an explosion. That would still be for us to work out. And before we could work it out, before we could even begin to improve the design in any way, we should have to understand, among other things, how the spaceship was supposed to work. Only then would we have any chance of discovering what might cause an explosion on takeoff. Prediction, even perfect universal prediction, is simply no substitute for explanation. Pause there, my reflection. So all of this, unfortunately, in my view, I don't know, I can't speak for David, but it seems to all arise from the same place. It came from quantum theory. It came from the beginnings of quantum theory, where physicists rightly were confused, befuddled. They didn't know what was going on. There was a whole swag of observations they were making that just didn't comport with what they already knew about physics. There were mysteries. And some of them simply retreated from reason. They said, well, the project is hopeless. We're very, very good at being able to predict the outcome of experiments, so that's all we can do. That's what science is about. Which is, I would say, less arrogant and more ignorant about science than anything else. It's as if to say the entirety of science is theoretical physics. And more than that, the entirety of science is those problems that you are unable to find answers to, solutions to, explanations for. And so therefore, from this observation, from your failure as a theoretical physicist in trying to understand this stuff, and you should be failing all the time. That's the whole point of science. You're failing, you're encountering problems and then trying to overcome them. But because of this failure, this specific failure, this failure in certain, rather at that time, esoteric areas of physics, you're going to extrapolate out to the rest of the entirety of science, as if all of science is just about predicting the outcome of experiments. It doesn't make much sense. It doesn't seem fair. It lacks consideration for all the other interesting areas of science where we really do want to understand what the heck is going on. People interested in astronomy and astrophysics, we love the explanation. It's a thrilling explanation about the evolution of stars. Stars like the sun and stars unlike the sun. And yes, those theories, those explanations allow us to give very rough predictions about what might happen to the sun in the future. Okay, absent people, of course. And we presume that what's going to happen to the sun in the future is it's going to end its life as firstly a red giant and then a white dwarf star, which will just slowly cool over billions of years. We know this. It's a fascinating explanation, especially in light of the fact of what else could have happened to the sun if it had have been larger. Namely, if it had have been a much bigger star, many times more massive, let's say 10 times more massive, then it would explode at the end of its life, leaving behind either a neutron star or possibly a black hole if it's bigger still. That explanation is the point of astronomy and astrophysics. This is why people do those kind of subjects. The fact that we can just collect light in telescopes and come to an understanding of the universe like that, an understanding of the universe, is phenomenal. That's the exciting part about science. Not predicting what's going to happen to any given star. It's the general explanation. The Big Bang Cosmology, cosmology still as a science is very much in its infancy. It's only been over the last few decades we've been able to actually gather data to some extent about the behavior of the universe as a whole. Prior to that, cosmology was well within the remit of theology only to deal with. It was metaphysical. How could we, human beings, pathetic as we are, presume to try and understand something like the entire universe, the entire physical universe? And yet this is what cosmologists take on. And by gathering these scant amounts of evidence, it's not like the most crucial part of cosmology is about predicting what's going to happen to the universe in the future. That's part of it. But the only way in which we can make any kind of guess about what's going to happen into the future, a scientific guess, a scientific prediction, conjecture about the possibility of what will happen into the distant future, is by having an explanation in the first place that relies on our understanding of what's causing the evidence that we gather. Evidence like the 2.3 Kelvin, or is it 2.7 Kelvin temperature of the cosmic microwave background, the heat left over after the Big Bang, which we've only recently been able to collect, these photons, these very low energy photons, and wonder about the origins of them, and explain, therefore, the origins of them. And so that's all the fun stuff. Putting together all the different, we're triangulating really with this heat that permeates throughout the entire universe, along with the fact that wherever you point your telescope at very distant galaxies, you find they're moving away, not only from us, but from each other. And trying to understand why is the amount of hydrogen out there in intergalactic space this amount compared to the amount of helium that's in intergalactic space, compared to everything else that's out there as well. Why is it this ratio? This triangulation of evidence that enables us to then come up with the grand explanation that we call the Big Bang and inflationary theory is phenomenal. That's the phenomenal part and the exciting part of the story of science, not predicting. And anyway, predicting these really distant things in cosmology, it's kind of, again, we're still in the infancy. And so whenever you hear science popularizers, it's kind of fun. I think it's about as fun as a science fiction movie at this point. There are, the predictions about what's going to happen to the universe on timescales of hundreds of millions, billions, even trillions of years, some of these predictions. And people make them very, very confidently. But the evidence is limited. That would be the first thing. And the timescales that we're talking about are just so ridiculous that it would seem to me that it's going to be the case that we're going to find far better cosmological theories. So at the moment, of course, we think that the universe is undergoing this dark energy accelerating expansion. And if we take that seriously through to the absolute limits of what we could possibly know, then we think, well, eventually all the galaxies that we can observe are going to wink out of existence because they're going to be accelerated along with space-time beyond the horizon of what we can see. Eventually only our galaxy will be left like a lonely island, and then it will start to expand itself as space begins to expand. And then, even the solar system will expand, and then, the planet will expand probably by this time, by the way. Of course, the sun has long since extinguished itself. But if any people are left here in the region that is the solar system, even eventually they will start to expand as well. Their bodies will start to expand apart because of this accelerating expansion of space-time. But this is all predicated on the fact that our theory, our present theory, the best theory that we currently have about the behavior of the universe won't be overturned. And I would, if I was a betting person, I would think that observation is going to be overturned in some way, in some significant way. And one possible way is that, even thousands of years from now, even if that explanation hasn't been overturned, that people might be able to harness the energy in some way and reverse it. Because at the moment, that accelerating expansion is actually quite a weak force. And that gets us very far away from the book here, except to say it's clearly not the case that science, in any field at all, is primarily about prediction. It's about understanding physical reality, and reality more broadly, and therefore it's about explanations. So even an oracle that's able to make all the predictions in the world doesn't allow you to really understand the world that you're in, even if you can predict the outcome of experiments, as David goes on to write. The oracle would be very useful in many situations, but its usefulness would always depend on people's ability to solve scientific problems in just the way they have to now, namely by devising explanatory theories It would not even replace all experimentation because its ability to predict the outcome of a particular experiment would in practice depend on how easy it was to describe the experiment accurately enough for the oracle to give a useful answer compared with doing the experiment in reality. After all, the oracle would have to have some sort of user interface. Perhaps a description of the experiment would have to be entered into it in some standard language. In that language, some experiments would be harder to specify than others. In practice, for many experiments, the specification would be too complex to be entered. Thus, the oracle would have the same general advantages and disadvantages as any other source of experimental data. And it would be useful only in cases where consulting it happened to be more convenient than using other sources. To put that another way, there is already one such oracle out there, namely the physical world. It tells us the result of any possible experiment if we ask it in the right language, i.e. if we do the experiment. Though in some cases it is impractical for us to enter a description of the experiment in the required form, i.e. to build and operate the apparatus, but it provides no explanations. End quote. Isn't that fantastic? Very much in David Deutsch fashion, just eviscerating what might be regarded as a knockdown argument against people who are saying that science is about predictions. Yeah, so if you had, it's almost like the super AI, okay, not AGI, but a super AI, okay, narrow intelligence, but it's a super intelligence. And this super intelligence can predict the outcome of any experiment that you like. And so this is what, some of the early quantum physicists, or about some quantum physicists still today, talk about being instrumentalists or the shut up and calculate type people. And if this is all that science is about, then this oracle would make, wouldn't it, science redundant. But the problem is, if you want it to predict the outcome of an experiment, then you have to first specify the experiment. That takes a heck of a lot of explanatory work to do. After all, why are you doing this experiment in the first place? What is the theory that you're testing? Have we thought about that yet? How do we input this in? How do we tell the oracle what the experiment is precisely? What is the instrumentation that you're using? How did you figure out what that instrumentation was? What is the problem that the instrumentation is trying to solve in the first place? And as David says here, well, we've got this oracle, don't we? We've got this oracle. It's called physical reality. Okay, physical reality is the oracle. It will give you the answer to any experiment that you ask it. The hard part is not asking the question. The hard part is figuring out what the question is in the first place. Asking what you're testing. What exactly is this theory you're testing? Why are you doing this experiment? This is not what science is about. Okay, we learn these terrible lessons in school science class. That what an experiment is, oh, well, we're doing an experiment today, class. We're going to take a test tube of these chemicals and a test tube of these chemicals, and we're going to mix them together into a beaker and see what happens. That's an experiment, isn't it? And in fact, this enters culture. This is what experiments are supposed to be. Just a random mixing of ideas, trying something where you've got absolutely no idea why you're doing it in the first place, let alone what is going to happen. And having found something new happening, something unexpected, which of course will happen in any case, you just don't know what's going to happen. You take your two test tubes, you mix them together. If nothing happens, that's surprising. You didn't know that that's what was going to happen. If you get an explosion, that's surprising. You didn't know that was going to happen. If you get a color change, and whatever the color is, it's going to be surprising. But the point is, you had no theory to begin with, did you? What were you testing? Why were you doing this experiment? This is not what an experiment is. I wouldn't call that an experiment. There is no sense in which that's an experiment. An experiment is a test of a theory. And there are two kinds of experiments in the world. There's an experiment where you literally have two good theories on offer, and you don't know which one is true. It's almost impossible to think of cases in science where there were three reasonable, viable explanations for a given phenomena. It doesn't happen. In science, just think about it yourself, there usually is identically one explanation, and we call it the scientific theory of. For so long, as far as the origins of the universe went, something that many people were interested in, there really were no viable explanations at all. There were supernatural ones, okay, God did it, which kind of raises the question as to where did God come from? And if people answer, well, God is that entity that's outside of space and time and whatever else, well, why move the problem one step back? Why not just say, well, the origin of the universe, whatever that thing was, is outside of space and time and gave origin to the universe. We don't need an intelligent creator being. Whatever the case, there were not really any good scientific explanations, at the turn of the 1900s, the turn of the 20th century. We had this idea of an eternal universe that was just always there, or infinite in all spatial directions. Maybe God clicked his fingers and a universe that was spatially infinite just popped into existence at some point. Whatever the Bible said, however long, 6,000 years or something. But this makes no testable scientific predictions. There's no experiment that we can do to test whether or not that is a better theory than something else. No observation that we can make. An experiment has to be able to compare two different competing scientific theories. And eventually we did have two. We had the idea of the Big Bang. The Big Bang sort of, it's an interesting part of the history of cosmology as to who came up with the Big Bang. Was it the priest George Lemaitre? Was it Alexander Friedman? Was it Einstein as well? They all seemingly had something to do with coming up with the Big Bang. I don't know where you would actually place the credit for the Big Bang itself. It was just this really was a case of the slow accumulation of problems and evidence in cosmology, which then all pointed to this common origin in the space and time. The universe was smaller in the past. But there was a time where it was quite reasonable to subscribe to Fred Hoyle's idea of a steady state universe, of a universe that just perpetually existed. So there was a genuine split in the scientific community. Was it an origin in space and time, the Big Bang, or was it a universe that had always been there, the steady state? And the purpose of an experiment, a cosmological experiment of a kind, of being able to observe things like the cosmic microwave background, that constitutes an experiment, setting up a big antenna that can collect microwave radiation, and to notice it is homogeneous in all directions, more or less. Which means that the universe is permeated with heat. What was the origin of that heat? Well, the steady state can't really account for that. Nor can steady state, of course, properly account for the redshift of distant galaxies in all directions as well. And then the ratio of hydrogen to helium. Okay, all of this stuff is explained by the Big Bang theory and not explained adequately by the steady state theory. And so these observations constitute experiments of a kind that rule out one particular theory in favour of another. Now, this is the ideal kind of experiment. The ideal kind of experiment is called a crucial experiment. It decides between two competing theories. Now, the only other kind of experiment is an experiment that makes a theory problematic. Well, maybe it doesn't even make the theory problematic. It's just a problem. The measurement of the speed of neutrinos back in the day, whenever that was, when the Large Hadron Collider was switched on, and they thought that the neutrinos were travelling faster than the speed of light. This is an experiment. They did this experiment. That experiment was problematic in the true sense of the word, not the woke sense of the word. In the true sense of the word, it raised a problem. Now, did it raise a problem for relativity? Well, it might have. It might have. As it turned out, no, it was problematic for another reason, namely the experiment itself was faulty, flawed. It suffered from something called systematic error. Okay, there was an error in the method, the way in which the experiment was conducted. A cable was loose or something or other. And so this is a legitimate experiment, in a sense. It revealed something about the nature of experimentation of that kind. Okay, careful with your cables. But that's the only other kind of experiment where you already have a theory. You have a theory about neutrinos and the speed with which things can move and the way in which an experimental apparatus should be set up, okay? And you're testing all of this stuff. You're testing this by conducting the actual experiment, collecting the data. But my example of, the random mixing of chemicals in a school science laboratory when you have no clue what's going on, well, that's not really an experiment. Now, to be fair, I don't think any science teacher actually really does this, okay? Most science teachers have some conception, at least, of what's going on with the underlying chemistry or science. And they do try and explain this to the children. And the children are, testing things. They are testing hypotheses. This does indeed go on. But the extent to which you're really getting a genuine understanding of what's going on is anyone's guess. That's a whole other topic, however. Okay, so I'm going to go back to the book. I'm going to skip a section there which is more detail about instrumentalism. This idea that the entire purpose of science is just about making predictions. And I'll skip to the point where David writes, quote, "An extreme form of instrumentalism, called positivism, or logical positivism, holds that all statements other than those describing or predicting observations are not only superfluous, but meaningless. Although this doctrine is itself meaningless, according to its own criterion, it was nevertheless the prevailing theory of scientific knowledge during the first half of the 20th century. Even today, instrumentalist and positivist ideas still have currency. One reason why they are superficially plausible is that although prediction is not the purpose of science, it is part of the characteristic method of science. The scientific method involves postulating a new theory to explain some class of phenomena and then performing a crucial experimental test. An experiment for which the old theory predicts one observable outcome and the new theory another. One then rejects the theory whose predictions turn out to be false. Thus, the outcome of a crucial experimental test to decide between two theories does depend on the theory's predictions and not directly on their explanations. This is the source of the misconception that there is nothing more to a scientific theory than its predictions. But experimental testing is by no means the only process involved in the growth of scientific knowledge. The overwhelming majority of theories are rejected because they contain bad explanations, not because they fail experimental tests. We reject them without ever bothering to test them." Pausing there, my reflection. Wow, there's just so much there, and I think this is again why, or a possible explanation for myself as to why I didn't get it the first time around. Even though I read this book, over and again, and I was engaged even in the late 90s in online email discussions about the book, I still failed to take on board so much. There's the concept of a crucial experimental test. This took me all the way until 2016, when David published his paper, The Logic of Experimental Tests, particularly of Everettian quantum theory. And it was then that I think I finally appreciated what a crucial experimental test was. There's a difference between a crucial experimental test and any other kind of experiment that happens in science. And again, the crucial experimental test is the one which is able to decide between a theory and its rivals. And so it leaves one theory standing, ruling out the others. Okay? And in most cases, certainly in physics, at best you've got two competing theories, at best. Usually you only have one. And if you do have one and you're testing that theory by doing experiments and the experiments aren't agreeing with the theory, then you've got this problem in Popperian epistemology, sometimes known as a Duhem-Quine thesis, of how do you know what's wrong? Is it the theory that's wrong when it disagrees with the experiment? Or is it that your experiment is wrong? There's that saying, many a beautiful theory has been slain by an ugly fact. Well, it's not quite true. You can't slay a theory with an ugly fact. Unless you've got another theory to jump to, unless you have a better idea of what to do. If we did 10 experiments tomorrow and they all disagreed with general relativity, there's literally nothing for it but to rely on general relativity because no one's got a better theory of general relativity, better than general relativity. Namely, a theory that can do everything that general relativity can do, and more. And more is the key thing. And there at the end of this section here, we get the idea that the overwhelming majority of theories are rejected because they contain bad explanations. Now this part I got back in The Fabric of Reality, and this is one of those thrilling passages because here we get to the grass cure for the common cold. This is the first time I encountered that argument. This idea that you need an explanation. It's the explanation that you're testing, not the predictions. Let's just read it. Okay, and this is where I'll end today because I think it's a great way to end things. And if you haven't heard this before, strap yourself in. Okay, the importance of explanations in testing, in experimental testing, rather than just predictions. David writes, for example, consider the theory that eating a kilogram of grass is a cure for the common cold. That theory makes experimentally testable predictions. If people tried the grass cure and found it ineffective, the theory would be proved false. but it has never been tested and probably never will be because it contains no explanation, either of how the cure would work or of anything else. We rightly presume it to be false. There are always infinitely many possible theories of that sort compatible with existing observations and making new predictions, so we could never have the time or resources to test them at all. What we test are new theories that seem to show promise of explaining things better than the prevailing ones do. Pausing there, ending it for today, but just notice there, anyone can come along and make a testable prediction, a testable claim. That doesn't mean they've got a scientific explanation. It doesn't mean they're doing science at all. David's other example is, any person with a sandwich board standing on the street corner saying that the world is going to come to an end in fiery bombardment from the heavens next Tuesday, June the 18th or whatever, has a testable prediction. Okay, and when the day comes and goes without incident, does anyone learn anything? Well, they might, or they might not. They might just go back to their religious text, reinterpret it in some way, and say, oh, I was out by a year, just you wait until next year. But there is no explanation there. It's testable, but without the explanation, we have no reason to assume why that prediction should be the way that it is. So if you say grass is going to cure the common cold, or eating 1 kilo of grass is going to cure the common cold, why should we believe you? What is the mechanism? And so this works for any area of science, and especially any area of pseudoscience, okay? Any quackery, anyone who has the crazy nostrum, the claim about what alternative medical intervention is going to cure you of your disease. The key thing is to ask why and how. Now, it's absolutely the case there are still places within medicine where there isn't a fantastic explanation of why the particular thing works. But in traditional Western medicine, certainly, at least what we have is a tradition of rules of thumb. In other words, this thing has been shown to work in many cases, and we don't know why. We don't know why yet, but we're working on it. We're trying to figure out what the explanation is. Okay, and I can easily, and we can, the community of doctors can show that the thing causes little harm and has some benefit for reasons they don't know. But this is because the gradual evolution, the hard-won evolution of that kind of knowledge, which we might even call inexplicit medical knowledge, that's been passed down, even if we don't have a fully explicit scientific explanation of how some of these treatments work. Okay, so this is the first of what I presume will be many episodes about the fabric of reality. We're barely through chapter 1 yet, and so next time I think I will read more, speak less. But until then, bye-bye. Now, of course, many people may well notice that if you're watching this for the first time, I have another series on the beginning of infinity, and importantly, alongside this, I have a series on the science of Ken and Kant, Chiara Mauletto's new book that has only been released over the last few weeks. This is in 2021. And so I'd encourage people to go out and get that book, as well as, of course, The Fabric of Reality. And if you're so inclined, you can find me on Patreon. You can do a Google search for Tokcast, Patreon, Tokcast, Patreon, and you'll find me there. Or Brett R. Hall at Patreon as well. Or you can just go to www.bretthall.org, and on the front there's a little button that says donate, and I would appreciate any kind of assistance with my ongoing work here in understanding the worldview of David Deutsch, Karl Popper, Chiara Mauletto, and various other people who are interested in the optimistic future and the centrality of people to understanding the universe, their cosmological significance. Until next time, bye-bye.